All right, with regard to the table, I had one more piece of paper here somewhere. Let's take a look at some of these. What I want this table to generate dialogue. A lot of your homework assignments are pretty individual things. You're sitting there working on a problem. Unless you're talking to yourself, you're not verbalizing. If you're all alone, maybe you are. Let's see, 2 divided by 4. Maybe you do talk to yourself. But I want this to generate discussion, okay? I want you to verbalize. So the point is not getting the answer. I mean, you do want to you want to move towards the answer, but the process in getting to the answer is part of this activity, this exercise. So consider this an activity. It's an opportunity to not only say this is what to kind of look at what I think in a particular case, but to explain why you think it. Follow me? In words to one another. So, I mean, even if if it's hard to get together or not, whatever, find some ways to get together and talk about this group. It doesn't have to be with the whole class. It could be with one other person, 2 other people, all of you, however you want to do it. What I was saying is you can decide whether one of you says, well, I'm going to take this, or I'm going to take volume, whatever, as the first swipe at it. So that individual will come through and say, well, I think volume increases in this case, doesn't change, increases, and someone says, why? Why do you say, I didn't think that, I thought the opposite, whatever. So use it to generate some verbalizing of your thoughts. Do it in pencil so you can adjust your answers. I'll have you each turn in a final one, and it may or may not be. In one case, there may be 4 of you that think it decreases, and one says, I don't think it changes. I don't agree with any of you. Whatever, okay? So you turn in what you think, and if you have an outlier from the other people, do that. So hand in one per student, and yeah, take till Wednesday. But let's take a couple.
Yeah, can we do like across the one example maybe?
Yeah. However you want to do it. I don't want to assign it. You can even talk about, hey, I'll do this first section here, or I'll do the ideal gas, and someone might want to. The ideal gases are always the easier ones. They're well behaved. We haven't said a whole lot about this, but let's just take a couple blocks. I said something about temperature. Now, what did we say on Monday about temperature? An ideal gas is compressed isothermally. So what happens to temperature?
It's constant.
Yeah, no change. Okay, so some of these things, there are some that are going to just fall out. You can go right down through there and say, isothermally. That means the temperature's not changing. That's the definition of isothermal. We didn't say a whole lot about kinetic energy. I think it appeared in one slide. One slide, I think. I've seen the slide. I don't know if I showed it to you, but we were talking about relationship between the Kelvin temperature, absolute temperature, and energy. Remember? Why do we use Kelvin? Well, because 0 Kelvin is 0 energy. Not that temperature is energy, but they are directly related to one another. You raise the temperature of something, you raise the energy. So if you're talking about a gas, you raise the temperature of a gas, and what happens to the gas? What happens to the gas particles, whether it be atoms or molecules? You raise the temperature.
They have more kinetic energy.
They have more kinetic energy. What does that? Yeah, they have more kinetic energy.
Moving.
And you can see that's directly related to their velocity. Their speed, the speed at which the particles are moving. You raise the temperature, the gas particles are moving faster. That was the whole thing about the balloon, blowing up the balloon. What's holding the balloon up is the gas particles hitting against the inside of the balloon. You heat that up, or you take the balloon, put it in the refrigerator, it shrinks. You take it out and put it in front of a heater, and it expands. The gas molecules are moving faster. They have more energy. So kinetic energy. Give me a column in there that you see a straightforward answer to. If the kinetic energy is proportional to the temperature,
Heated at constant volume.
okay, it's being heated. Where do you see that one? Heated at constant pressure.
Up from the bottom.
For
Ideal gas is heated at constant volume.
okay, well, it's being okay. So what's going to happen then? Heated at constant volume. Ideal gas.
Pressure would increase.
No, just with regard to kinetic energy.
Well, it's being heated, there's more energy going in, so kinetic energy should increase.
Okay. So if you're heating it and the temperature is going up, kinetic energy should increase. You got an ideal gas. If a real gas is expanded isothermally, what, again, kinetic energy?
No change.
Say no change.
No change? Okay, I'm just, just want to fill in a couple here. Let's look at the term adiabatically. Do you see any category here where the term adiabatically, insulated, totally insulated, so no heat is coming in or going out?
So Q is no change.
Okay, Q, no change.
But temperature, can temperature change?
Technically, based on pressure, your temperature is going to change.
Yeah. So if you're compressing it,
Because it's expanding it, so there your temperature should decrease.
yeah, if you're expanding it and it's adiabatic.
You're looking at that second one? A real gas is expanded adiabatically.
Yeah.
So Q is no change. So I got the right line here.
Temperature decrease, I think that's what I thought.
I would say temperature decrease.
Yeah, it should, an expanding gas should cool. Okay, so there's just a few toe holds to get in there.
Should the kinetic energy column match the temperature column if they're directly proportional?
Probably. Yeah, I think so. Yeah, I think kinetic energy and temperature would line up.
Can we talk about potential energy?
Yeah, that's
That, we could. That's the deepest waters.
So I'm just wondering, like, what do you mean by potential energy, like within the bonds of the atoms that make up the gas?
Probably. I
Or is
think
it
you're
like-
starting to get into the right territory.
pressure.
We'll even look at a couple slides today. Where does the enthalpy come from? If a gas burns and it releases heat, where's that energy come from? Well, there's potential energy in the covalent bonds that are holding the molecule.
So in theory, the potential energy is not going to change for anything. Unless we're combusting.
I think it has to do with pressure. Like the molecules under higher pressure have higher potential. Is it like potential energy of the molecules or the molecules to do work on something? Right, like things under higher pressure.
These are all good. I need to think about it some more, but that would be getting back to Grant's comment for a second, that the potential energy, would you say it wouldn't change?
It wouldn't change if we're talking about the amount in the bonds, unless you combust it.
Right. But that would be an oversimplification. I think what you're saying might be true for an ideal gas, but for a real gas, where there may not be a covalent bond, but there's an attractive force between them, that's where potential energy will get involved.
Most we're not talking about the sigma bonds. We're talking about IMFs.
Hydrogen bonding.
Okay.
Okay, you say sigma bonds, you know there's a bond energy in there.
Yeah.
Well, now a hydrogen bond doesn't have as much energy as a sigma bond, but there is some energy associated with the formation or the breaking of that. So on real gases, why am I saying ideal gas? You might be right.
Because you don't talk about IMFs in an ideal gas, because you pretend like they don't exist.
Yeah, one of the assumptions for an ideal gas is there are no interactions between the gas particles. There are no forces of attraction or repulsion involved. So, yeah, let's leave that one. Think through some of the other ones. This one is a little harder to grasp and harder to explain. But
are there any other columns that real and ideal gases would be different? I guess that you could think of.
This would be proportional pressure.
Other than potential energy.
I think so, but I don't know offhand. One other one that could fall out in some cases is work. Where would I guess if work were zero, it'd be no change.
Anytime something says cool, anytime there's gonna be if you say you're using a piston or something, there's gonna be change, and there'd be a work change. Cool at constant pressure, that would mean your volume would have to be changing because your gas is contracting.
So that you have work. But if you're doing things at constant volume,
there'd be no work.
There'd be no work. Okay, so those are some hints, some things to get started on. A lot of different situations here, but just to start wrapping your mind around, okay, where's heat involved, where's work involved, where is work not involved, how would that affect internal energy, enthalpy, etc. Okay, enough of that. And Monday, if you have some more questions about that, or if you want to ask about something, or you've been discussing it, and we can talk about it some more. Okay, did I give you these slides? No? Not yet. I printed them a little bit differently. There's more of them, so I didn't want to use as much paper. It makes it a little bit smaller, but at least you got something, and I'll have one more thing to hand out in a second here. All right, some of these slides I'll run through real quickly because we've already seen them, and then I want to spend a little bit of time on heat capacities and then a lot of time on enthalpy today. That's where I'd like to go. And then at least have in your hands about everything you need to do the homework. Okay, we talked about this. The heat, the mass times the specific heat times the change in temperature. For just anything, heating up a cup of water, heating up a chunk of aluminum, whatever. You can calculate the number of joules associated with a temperature change if you know the mass of the object, if you know the specific heat of the object, and you know the temperature change. It's a fairly straightforward equation. We talked a little bit about calories. This is how the bomb calorimeter would be used to find out the delta H of combustion. You can burn an apple. You could burn, you don't get a whole lot of calories out of it. You can burn butter, get a lot of calories out of it. Calories per gram. That's the nutritional calorie, which is 1,000 calories. So 1 calorie is 4.184 joules. 1 nutritional calorie is 1,000 calories, 4,184 joules. You can see how small that really is. I mean, that's the amount of heat necessary to heat 1 gram of water 1 degree centigrade. That's a small c calorie. All right, a constant pressure calorimeter. We're going to look, we got these CPs, constant pressure heat capacities, CVs, constant volume heat capacities. Most everything done on a lab bench is done at constant pressure, whatever the pressure happens to be that day. Typically around 1 atmosphere. But this is a constant pressure calorimeter. So whatever's going on inside of there is going on at atmospheric pressure. It's adiabatic to an extent, as well as a styrofoam cup can be, or a really good calorimeter. But so this is the typical simple calorimeter where you just carry something out at atmospheric pressure. It's not complete. It's not particularly sealed. If there's a gas evolved here, it can evolve out of there. It's not being pressurized in there. So yeah, you can carry out a little system inside the calorimeter and do some things. We talked about the first law of thermodynamics, the internal energy of the system plus the internal energy of the surroundings is zero. There's no creation or neither creating nor destroying energy. Now here's a bomb calorimeter, and I don't know that I've ever really seen one. I've never done any experiments in a bomb calorimeter. But a bomb calorimeter is constant volume calorimeter. So you have this sealed chamber in here that is actually submerged in water. And so you have a certain bath of water right there. If it was a Big Mac you wanted to burn inside there and figure out how many calories it had, you put the Big Mac in there and then zap it and burn it. It would give off some heat. The heat would dissipate into the water temperature would go up. And how would you figure out what that is? Well, this calorimeter ends up having a certain heat capacity, depending upon how it's designed, how heavy it is, how much water is in it, all that sort of thing. So this might only go up a half a degree, but it was actually a lot of energy because there's such a heat capacity to the entire calorimeter. So you're going to relate this temperature increase to the energy released by whatever you burnt in there. So yeah, there's a constant volume and a constant pressure heat capacities. Sorry, I usually turn this off. This is Northwestern. Nazareth Hall is experiencing a water outage. See email for more details.
Yeah, I didn't get that email. Oh, not cool enough.
Oh man, I feel so much better already. I didn't know I was that well connected. I got the email before a student.
Been here for 3 weeks, gets emails, so here we go.
I was teaching in Texas, and one day there was actually a threat in one of the other buildings, and I'm teaching, and about 8 or 10 of my students all of a sudden they were saying they were evacuating this other building on campus, and they're all getting it on their phone, and they told me.
So what'd you guys do?
We were not evacuated. Our building was. They had clamped down or shut down this one building there. But it did end up interfering with classes the rest of the afternoon. Okay, at this point, I want to just switch over to this. This is right out of the, well, it's not right out of the text. It is out of the text. And Dominic, I think it was the first day of class, you said, did everybody get one? Yeah. The first day of class, you said, do you expect us to derive these equations? And I think probably not. But I did want to just pause on this one for a second. This is all, forget what pages this is, but this is deriving the CV, the relationship, what is CV and how does it relate to the internal energy. Starts with equation 221 and goes down through 227. And I just wanted to point out a couple things and leave it at that. Okay, so kind of what we were doing, at one point on page 38, the author makes the point that if you work with a constant amount of gas, let's say 1 mole, then according to the ideal gas law, if you set that as a constant, you really only have 3 variables: pressure, volume, and temperature. And then he makes the point that if you know any 2 of those variables, you could calculate the 3rd one. Okay, because they're not all independent of one another. There's a connection. So if you know 2 of them, you can determine the 3rd one. And so he said for internal energy, the 2 that are chosen, you could choose any 2 arbitrarily, but it's convenient with internal energy to choose temperature and volume. And with enthalpy, it's convenient to choose temperature and pressure. Okay, so just follow page 30. You can kind of look at this on page 38, 39, 40, basically. So you're choosing temperature and volume for internal energy. And so the complete differential is the differential of the internal energy is the partial of the internal energy with respect to temperature, constant volume, and the partial of the internal energy with respect to volume at constant temperature. So this is just very similar to what we did when we were doing the differential for pressure on the ideal gas law and temperature. And then earlier on, this relationship that the du equals dq plus dw. So du is equal to dq minus pdv. You can substitute that in so that I need a pointer. That differential there is equal to du. du is equal to this, so you end up with that equation. So it's just rearranging it. And then saying at constant volume, this goes to 0, and you get that. It simplifies down to that. Constant volume, this is 0, so that whole thing falls out. You get dq equals a partial u with respect to temperature, constant volume, times dt. And just one point here, notice that what he's doing to go from here to here is just dividing both sides of this equation by dt. Divide this by dt, you get dt. So you get dq over dt is that. And just to make the point that you can treat this like that. So you got dq over dt equals the partial of the internal energy with respect to temperature at constant volume. And this is that. So dq equals cv times dt. And if you integrate it, you get the delta u is equal to cv times delta t. All right? I don't expect you to derive that, but to just kind of just see how the math is falling out, how you can rearrange these equations to get down to an algebraic equation. Delta u equals cv times delta t. So really, at the beginning of the class, at the beginning of the course, we talked about we're going to get into more calculus. Well, there's certainly calculus involved in getting to these endpoints, but many different parameters are put in there to simplify it down to some useful algebraic equations. I'm missing something here. Oh, go all the way down. So you think that, so that's true, or in terms of the molar heat capacity at constant volume, get this equation. Okay, that looks useful. What makes it a little more cumbersome is the fact that this varies with temperature. Heat capacity varies with temperature. So even when you look at, and I don't even think the book has a really good table of heat capacities, but if you look up heat capacities, you'll see they'll have the heat capacity of helium at different temperatures. At 0 degrees, at 100 degrees, 200 degrees, different degrees. So that there's actually a relationship there. How do I expect you to use this? Well, on some problems, and I think maybe there's one example there, just kind of using some of these equations to solve the problem. I left some of those blank pages there to either fill in some of this or try to copy some of this in there. But okay, let's get back to enthalpy. Oh, and then there's the Joule-Thomson coefficient, and again, you don't worry about deriving that, but just maybe simply using it on some occasion. Let's see if this problem. This is an enthalpy problem. No, this isn't going to use Joule-Thomson. I don't know that I have.
I've got a question for you.
Did one of the other problems have a use of Joule-Thomson? Not that one.
You gave us this equation which is almost identical to this delta U. How are they different? The one that,
Q stands for energy.
well, yeah, but this equation right here that you gave us, C times delta T, it equals delta U.
Yeah, no, that's not a C sub V. That's just a
It's just heat
straightforward heat capacity. So C is equal to, this C is mass times specific heat.
capacity. Okay.
This is specific heat of the material,
Oh, got it. Okay.
and this would be how much material is there times its specific heat.
Okay.
So yeah, that is a different C than these CVs and CPs.
In a different class I took, we talked about CV and CP. CV, you didn't have to have constant volume pressure processes, and CP, you didn't have to have constant pressure processes. Are we only treating that CV can be used in constant volume processes, or can it be used in any process?
Well, I think in any, the author goes on to show a relationship between CV and CP. What you were saying that you taught, a CV didn't have to be in a constant volume?
Yeah, it didn't. It could be anything, same with CP.
Yeah. Yeah, I think that's the case. I think there'll be some situations where both capacities are involved.
Okay.
I don't think any of our problems will get that complicated. Okay, let's talk a little bit more about enthalpy. All right, so where does the chemical energy come from? It's stored in the bonds. If we had this general chemical reaction and change these compounds into these compounds, and what either released energy or absorbed energy, why that energy difference? Well, it has to do with the nature, the energy associated with the bonds in these compounds versus the bonds in the products. And so if there is more energy in these bonds than in those bonds, then there's going to be energy released. It'll be exothermic. And if the opposite is the case, it'll be endothermic. As this converts to that, it will actually have to absorb energy. To do that, it would be an endothermic reaction. Just quickly summarizing that. So if we had methane, let's see, this one, methane plus oxygen. There's a lot of energy stored in these bonds going down to carbon dioxide and water. There's less energy in a carbon-oxygen, hydrogen-oxygen bond than what's in these bonds. And the difference is the amount of energy that's released. All right, and then we show that as negative. So really the system is losing that energy. The original system is losing energy. It's exothermic. It's releasing the energy to the surroundings and heating up the surroundings. And the reverse of that here, where ammonia is decomposing back into its original elements, nitrogen and hydrogen. So this is at a lower energy. It needs to absorb energy to get there. The system is gaining that amount of energy per mole change. So this is enthalpy. So from here to here, kilojoules, these numbers look a lot different than the previous one. I don't know what the difference is here. We had 211 heat given off by the system of surroundings per mole. It seems I'm seeing a discrepancy between those two.
The other ones are kcals, and these are kilojoules per mole.
Okay.
Yeah.
Good. Different units. Okay. I got caught up with the numbers. Great. So just showing that in another way. Delta H is less than 0. The enthalpy is dropping. Phase changes have this associated with it as well. So for ice to melt requires energy. All right, Hess's law, I think you are probably familiar with Hess's law. These are just quickly going through. If we write an equation one direction, so to go from there, it requires 6.01 kilojoules per mole to melt ice. For water, liquid water to solidify is going to release 6.01 kilojoules per mole. So, and if you double it, twice the amount, twice the energy.
So what is Hess's law exactly? Just so you can, if you go backwards, it's just the negative of that voltage.
Well, Hess's law is coming up here. It's a little bit more than that. Hess's law says that if you did a reaction in steps, it's the same as doing it all in one fell swoop. That's Hess's law. We'll look at that in just a second.
You have like 5 equations and move them around and add them, and then you come to a final delta.
Sounds familiar.
You'll see.
Yeah. Okay, let's talk about these standard heats of standard enthalpy of formation. Oh, let me just point out the book. I don't know. I've never seen this before. He writes it this way. You probably are familiar with seeing that. So I'm going to use this. All right. This is what you see in the book. I think he even has this delta H delta F of H, which is which you'll see me writing, delta H of formation with a degree sign on it, meaning it's standard conditions. The delta H at standard conditions. Taja?
Computer is kind of everywhere right now.
I was really enjoying it.
Were you enjoying that? What happened?
It just
This has got a magnet on it. I laid it down here, and
oh,
so where did we go?
you went to the end of the slideshow and zoomed in and did fun stuff. Or?
Not resistance.
Mind of its own. Okay. Thank you. All right. Well, when I say I put the lectures up there unedited, you get a treat. You get treats like that.
Nice, thank you.
Yeah. If I had an IT department helping me out with my lectures, that'd look better. Okay. Now let's take a look at standard enthalpies of formation. There should be an F under there. Put an F under there. Delta should look like this. Delta H of formation. And what are they? Think about it, for example. I don't know what altitude Minneapolis is at, or St. Paul. Anybody know what our altitude is?
We're about 900.
900 feet. With respect to what? Sea level. Okay? So when we talk altitude, we have this reference point. We have this reference point, which is sea level. If we wanted to, it could be relative to the highest building in Chicago. I mean, you could take it off of any point you wanted to, but sea level seemed to be a pretty reasonable point to say. The Dead Sea is actually about 1,000 feet below sea level. I think it's the lowest point in the Earth below sea level, other than something below the ocean somewhere. So there is the Dead Sea. You could have said, well, let's measure the altitude off of everything from the level of this Dead Sea. But they got sea level. Well, here's what we're doing here. We don't know, altitude is always relative to some kind of 0 point, arbitrary 0 point. We're taking an arbitrary 0 point being the element, the enthalpy associated with the element in its standard state. 25 degrees centigrade, 1 atmosphere pressure. How does that element exist under those conditions? Its delta H of formation is 0. What is it? What is the absolute value of its enthalpy? We don't really know. But we're taking that as our 0 point, and then we're working off of that. So the delta H of formation of oxygen at 25 degrees C, 1 atmosphere pressure is 0. ozone has a actual delta H of formation. Graphite and diamond are both pure carbon, but graphite is the kind of the standard form, more common than diamond. So that's the common form of that element. All right, so these are delta H of formations. You do have these in the back of the book. Here's just some examples of them. So what we got here? That's liquid. Oh, that's hydrogen peroxide. Oh, okay, that's fine. That's fine. I was going to say, why isn't that zero? It's not zero because it's not an element. It's a compound. But if we take hydrogen gas, 0, zinc, solid zinc, 0. So the elements are 0. Any other form of it, so hydrogen atoms, it takes energy to split these apart and get them back into individual atoms. So the elements are always 0. They're standard conditions, and then you have things like water. This is a delta H of formation of liquid water. That's its standard. At standard conditions, that's how it exists. It doesn't exist as a gas. It exists as a liquid. All right. So a delta H of reaction. So this is a key equation for calculating the delta H of reaction. It's the sum of the delta H of formations of the products minus the reactants. That's it in general terms. But you can see you have to work off of a balanced chemical equation, and you're bringing the coefficient. So this is going to be, here's your products, C times the delta H formation of compound C plus D times the delta H formation of compound D, that whole factor, minus A times the delta H formation of the reactant A plus B times the delta H formation of reactant B.
What's lowercase m?
Where is lowercase m?
Bottom line, on the right-hand side.
That should be,
It's just coefficient.
Because I think the n standing for moles.
Yeah.
Moles also.
maybe that should be an N there too. Yeah, probably just in, yeah. These are just standing for these coefficients, the molar value of them. Well, let's just take water quickly. Let's go back to this table. So the delta H of formation of water well, okay, you can't, it wouldn't do that because those are all going to be 0. Yeah, that's just going to come out to that number. But if we had I think I'll get a simple. I'm still sticking with my M right there. Okay, Hess's law says when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So here is a good example. Why is this a good example? Well, you can take graphite and burn it and produce carbon dioxide and water. I guess I should have water down here. No, just CO2. We're burning the graphite and forming carbon dioxide. So to go from there to here, the delta H of formation of carbon dioxide is minus 393.5 kilojoules per mole. You can take carbon monoxide and burn it. I mean, you could do this and experimentally determine this heat, this change in enthalpy, the heat associated with that. Taking carbon monoxide, burning it to form carbon dioxide, minus 283.0 kilojoules. But imagine for a moment the experimental difficulty of burning graphite to produce nothing but carbon monoxide. Okay, that's difficult to do. It's difficult to do because you're burning carbon in the presence of oxygen. Yeah, if you have a deficiency of oxygen, you get some carbon dioxide, but some of that carbon monoxide is going to react with some of that oxygen that's available and produce carbon dioxide. So it's really very, very difficult, if not impossible. I won't say impossible because there's probably someone trying to figure out how to do it. And maybe they've already figured out how to do it, but very, very difficult to burn carbon to produce nothing but carbon monoxide. So you'd say, well, how do I get that delta H of reaction? And this is where Hess's law comes in. Hess's law is basically saying it doesn't matter if you go from there to here in one step, or if you go from there to here and from here to here in two steps. The sum total of the change in enthalpy will be identical, exactly the same. And this is getting back to what we've been saying about state functions. Enthalpy is a state function. Doesn't matter the path you take to get there. If you get to the same place, it's the same change in that state function. And so you could take the energy associated with this minus the energy associated with burning carbon monoxide and calculate this delta H of reaction. So the minus 393 minus the minus 283 gives you a value of 110.5 kilojoules for that top reaction. Right, which is what that is just showing right there. Okay, so that's Hess's law. You've had it, I'm pretty sure, and that's a little review of it and how it fits in here. There's a couple, there's going through those examples a little bit more. There's a delta H of formation of acetylene. Calculating the delta H of formation of acetylene from different things. So all right, let me give you these other problems. Some of the other slides attached there we've already gone over, or we've gone over the concepts of work. So if you want to staple those into your, see, did I keep myself a copy? Yeah. So let's take a look here. Problem number 3 is, it's really designed to convince you to recycle aluminum cans. Okay, that's the purpose of problem number 3. And you use two equations, very simple equation, what's the heat associated with melting a mole of aluminum, and then 3b is looking at the delta H of reaction to form aluminum from bauxite ore. And so that you can just use the delta H of reaction. Yeah, see what that reaction would be. On the delta H of reaction in the equations, you have to follow the signs real carefully. Yes?
So are these two new questions, are they homework 2B?
Yeah, that's homework 2B. Right. Exactly.
On here it says, calculate the delta H reaction, yada yada yada. The according to the following reaction.
Oh,
There's
oh.
no following reaction.
Okay, let's give you a following reaction,
Oh.
and then balance it. Good, good, good. It's a good thing we're going over this. Left out something fundamental. So yeah, you want the delta H of reaction for that reaction. Now keep in mind, you got to balance that equation before you jump off onto this, because those coefficients fall into that delta H of reaction calculation. Very good question, Grant. I'll have to add that to this. Okay, number 4. Let me just make a comment about question number 4. It seems to me, and I did this problem, but I didn't do it 2 ways, but it seems like you could do it 2 ways. You could go through and calculate the delta H of reaction of this. And it says there, calculate, you can see the authors, because I just clipped this right out of the book, delta reaction H. So it says calculate the delta H reaction. It also says write out the formation reactions that add up to. Okay, so if you do it both ways, that first statement there, write out the formation reactions that add up to, is really approaching it from a Hess's Law point of view. Kind of what are all the different reactions that you could manipulate around this, and then you could add up the delta H of formations, and they should add up to what you get for the delta H of reaction. Okay? You'll have to think about it. But, I mean, if you consider it for a minute,